Our first talk is by Ritoban Thakur, and he's going to be talking about BICEP-Array.
Am I audible? Okay, all right, cool. To you, yes. Okay, yep, so it's a great opportunity to come back to my home country and talk about what I've been doing the past few years. So I'm now a member of the BICEP-Keck collaboration, which, as you know, is the set of telescopes trying really hard to detect the inflationary gravitational waves. So let's see, so this is just a photograph of all our collaborators on the BICEP-Array project. It's largely led out of Caltech, Harvard, Minnesota, and Stanford with great collaboration with various national labs like JPL, NIST, and so on. So this is a bit of a review for people who don't think of the CMB from the instrumentation point of view. I'm an instrumental person. So the way we kind of see the CMB in a strawman sense is you have a radio antenna of some sort with some polarizer in front, and you point that to the sky and you do a scan and right ascension or declination, and then the power that you collect in the microwave band is dumped onto a detector where you measure some temperature. And this, when you translate it to the perturbations and not the constant value of the temperature, have interesting physics in the anisotropies, both in the raw temperature and of course in polarization. So this is a plot for the B-mode map from BICEP, released a few years ago. And this is what it looks like in real life. So you see the tilted lines, and these are showing the sense of the polarization that we measure. And you see the swirly pattern, and this is the archetypical signature of what we mean by B modes or curl-like modes. And effectively, you can think of this as a Helmholtz decomposition into divergence and curl, and this is that curl nature of the spatial field we are measuring. Okay, so I am not a theoretical physicist, but I owe it to describe in one quick slide why we are going after this and why we should see something. And the basic premise is that if you have density perturbations that are in this manner of low, high, then you get this dipole pattern, and that when you combine the fields from many swaths of the sky, you end up with something that looks like a divergence and called E-modes. And similarly, you can have essentially quadrupole anisotropies, and there can be multiple sources of this. One, of course, being the perturbation of the space-time caused by inflation, which would then lead to these curly patterns, whose real picture I showed you before. And so this is the connection between what we measure and how it gets to be there in the first place. And the big statement is that the power we have in such swirly patterns on the sky is a direct probe of the tensor to scalar ratio, which is essentially the physics of inflation, right? So when we can measure this stuff, we can directly comment on the physics of inflation. So that's a very quick science justification. Okay, so in terms of where B modes lie with comparison with other polarizations and the CMB itself, you can see that it's actually very low. So the temperature anisotropy, famously measured by Kobe WMAP and of course Planck with tremendous precision, is all the way up here. And then you have a lot of power in the EE spectrum, or the one that looks like the divergence pattern. And then the B modes are far lower in this log plot. And even there, the inflationary ones, we don't know what the scale is, but they're somewhere in this gray band, could be even lower. But on top of that, you also have B modes that come from the intervening matter potential between the CMB at high redshift and us today. So this is only to demonstrate the point that we have to go in sensitivity a long way to be able to probe this interesting physics here. So one of the main challenges that you get to when you're trying to measure these B modes is the lensed B mode. So this will be there, and it is there, whether we have a measurable R or not. And the idea is that you have the CMB, the photons are coming, but there's a lot of volume between us and the CMB, and in that volume you have clusters of mass, and you have effectively gravitational lensing where the shear will cause a change of the E modes into B modes. So this is sort of a warping of the picture by an intervening set of lenses. And that is what causes these B modes that we have now measured. So the E modes here, because of the matter potential, get lensed and become power in the polarization of B sense. And we have to, effectively get rid of this if we were to dig down further and look for the inflationary gravitational waves. So this is a challenge in our field. Another challenge, as mentioned repeatedly, is that of foregrounds. So this is an old picture from Planck, only to demonstrate the point that away from the CMB main or peak frequencies of order 100 gigahertz, at low frequencies you have a lot of contamination from synchrotron, and at high frequencies you have contamination from dust. And these are not unpolarized, they have some polarization from fundamental, the physics of the source, and they will leak into our maps, and we need to do foreground cleaning. And this is, again, a vast scale in magnitude, so it is important that we do this foreground clearing in a very sensible way. Same thing plotted, not in spatial sense, but in spectral sense. This is only in temperature, but you see that the foregrounds are pretty broadband, so they're not individual lines that you can, select and clip. And we don't know what fraction of them may be polarized where in the sky, and this can cause the challenges that I mentioned. Okay, so BICEP Keck has been in this business for a while, and this is a set of telescopes that have been designed particularly to find the B modes from inflation. And the generation of telescopes is just shown here. It started with a somewhat smaller focal plane, and we are going towards a newer generation of what we call BICEP-Array. And this will have 4 frequency bands that I'll show later. And this will be basically replacing the Keck array at South Pole. And with ever increasing population of these low noise superconducting detectors, we can map the sky with very high sensitivity. This is just a generational scheme. So a quick flash. So there was a recent paper that came out analyzing data up to 2015. And this is the best limit on R, or the scale of inflation that we have so far. So here, what you're seeing is degeneracies in the measurement of R that you have to deal with. Namely, R itself can have dependency on how you measure and fit for dust and synchrotron. So the capital A's here are the amplitudes, but then the spectrum of the dust or the synchrotron will have not just an amplitude, but also a tilt. And these are parameters you have to think about. And these are basically the priors that go into the likelihood for these indices in spatial and frequency sense that are being shown here. And additionally, we also include a spatial correlation between synchrotron and dust, because if you have more stuff in some part of space, it is likely it will cause both of these populations. And so, this is the kind of thing we have to deal with at the tail end of a lot of data taking and analysis. But the point is that R itself has to be disentangled from all of this other stuff. Okay. So driving that point more seriously and not with cartoons, this is the sensitivity computed in a band power around L of 80, where the B modes peak. And what we are showing here is, driven from BICEP's historical measurements, what is the limitation that you will get from synchrotron and dust. So in the BICEP patch, with the 220 gigahertz receivers and cross-correlating with Planck high frequency, there is a very decent measurement of dust. And so there is a sensitivity line that you can get with some error bar. Synchrotron has not been measured in that sense by BICEP Keck, because we just didn't have a low frequency channel to capture the synchrotron, and therefore it's just an upper limit. And in this plane, you can put down all the data that we have measured, cross-correlating with Planck and WMAP and so on, and ask where is the limit today and where we need to go. At the moment, the limit is again in the synchrotron. We need to beat this first, and then dust, and of course the CMB channels keep taking data the way they do, and that lever arm gets you to measure R very cleanly in the main CMB band, okay? So with that in mind, this is the introduction to BICEP-Array. So it will be a set of 4 receivers, and the 4 receivers have the following designation with frequency bands. The first receiver will be dedicated for synchrotron measurement at 30 and 40 gigahertz. And then we have 2 more at the usual CMB numbers of 95 and 150. And then in the a couple of years or maybe 1 year, we'll have the dust receivers, which will measure the CMB at this high frequency where dust dominates. This is a CAD drawing of how the receivers will be placed in a telescope mount. The really cool thing is not only do you have rotation in this axis and tilt, but each of these receivers will rotate around their bore site, and that allows for very clean systematic correction with polarization. This is the assembly at University of Minnesota. This is largely Clem's efforts, where the receivers will go in. There's a color change between CAD and real life, but this hexagonal thing is that hexagonal thing. Okay. So what goes into a receiver? So when I was coming for this workshop, Rishi suggested that I lay out what really happens inside these telescopes and walk through that in some manner. So this is the BICEP-Array receiver, and I will say that it is not dissimilar from what we did for SPT3G. So they have a very similar underlying engineering problem. So you have some form of a window, a telescope window where the light must come in. But because this is microwave light and you do not want high frequency or optical or UV and IR, there are materials that are carefully chosen to do this, light transmission and focusing. And then down here you have the cryogenic detectors that are cooled at 300 millikelvin with these special helium sorption fridges. And the whole thing is one receiver. That's the language we use. In addition, we encase all our detectors and amplifiers with a niobium tank that I'll show you later, a cup. And this is to shield it from magnetic fields that can get in and pollute our signals. So this is the innards of it. This is that niobium shield with the detector focal plane inside. And then this is all held at different temperatures by carbon fiber legs. And that does the separation in temperature while maintaining the structural integrity. This is what the focal plane will look like. It will be a checkerboard pattern with detectors measuring 30 and 40 gigahertz. And all of this assembly gets called the sub-Kelvin camera. This is what it looks like in real life. We have been testing this exact receiver for the past few months. It's called BA1 because it's the first receiver. This is the pulse tube assembly. The window is here, and there are various coils of cable going for systematic testing. This is our team at Caltech, half of our team at least, and this is that same focal plane with the carbon fiber assembly that I just showed before, but in, again, real life scaling. And so we are doing a very serious campaign now in our lab to see what kind of external factors can affect the measurement of these very sensitive signals inside with cryogenic performances, magnetic pickup, microphonics, and so on. This is again a picture of all the parts. So here is the fridge we get from France. This is where the detectors will sit. There's only one guy now at the moment. This is a detector tile fabricated with superconductors on silicon coming from JPL. And these are some special submillimeter optics that we have to install and test. So on the detector front, BICEP, like SPT and several others, use transition edge sensors. So these are bolometers, and the method is simply this. The power that comes from the CMB is absorbed in something, and that thing remains hot for just a little bit with this weak link, and you have effectively a thermometer that can measure how much power has been dumped, and that is effectively the temperature of the CMB falling here. And that temperature is changing because the telescope is scanning across the sky and seeing the anisotropies on the sky. And this is an antenna that does the collection of the CMB and pass that signal onto the detector. So this is a first level data that we just collected in our lab for one of the 40 gigahertz focal plane, tiles. So this is a twin slot antenna that is doing this 40 gigahertz photon collection, and then it's getting measured by the transition at sensor, and this is showing a very sharp transition of many detectors here, which is to say it works. And we know it works really well when we have made the plot that tells us what is the frequency coverage of these detectors. And you see that it's doing a decent job covering the 40 gigahertz band that we intended. This is the first preliminary tile, and there's a lot of fabrication back and forth that will happen to make this a little better. But this is a very good start. Okay, so what's the big plan? So there's a lot of numbers here, and I will keep this up at the end of my talk. But the big plan, again, is to cover a sky area that is similar to BICEP-3, but this time with many more detectors, and at the frequencies that I have mentioned for taking care of foregrounds and not just the CMB. And there's a pretty decent level of NET or noise equivalent temperature, which we will reach. I should say we hope to reach. This is a canonical sensitivity plot for R that shows historically how sigma R, the error on R, has been coming down with time with ever improving generations of detectors and telescopes being fielded in the BICEP-Keck collaboration. And you can see when the 30-40 gigahertz synchrotron is deployed, there's going to be a very rapid change there. And then eventually we will need to do the delensing to get to the raw sensitivity. And this is the last slide of my talk on what we mean by delensing again. So here we are not alone. We are in collaboration with the South Pole Telescope, which is our neighbor. So that's BICEP-Keck, one of the BICEP-Keck stands, and this is SPT. So SPT is a CMB telescope that is measuring the CMB in a very similar band of colors, but with much higher angular resolution because they have a different set of science goals. And because of the high angular resolution, and the fact that they're also measuring it in E and B polarization, we get a very clean picture of the lensed B modes. And then in analysis, one will have to do the delensing. This is an extremely optimistic projection from SPT-3G, but this tells you how much you can go if everything were to work perfectly from the unlensed to the delensed version of these gravitationally lensed B modes. And this is important because the moment you come down here, you get to see the peak of the inflationary gravitational waves, which is our target. Yeah, so with that, I'll end and take questions because there's a lot of instrumentation details. And the punchline is really that the BICEP-Keck program is just dedicated to going after R, and we have realized the hard way perhaps that foreground measurements are very important. Therefore, we are deploying separate foreground measuring telescopes, and in collaboration with South Pole Telescope, we will be able to do this kind of a delensing and push down the limit on R to a few times 10 to the minus 3. All right, thanks.
Okay, questions? Joe.
What is the typical yield end to end from the moment the wafer comes out all the way to on the sky?
I don't have a good answer for BICEP because I'm very new to the collaboration.
I can answer that.
But yeah.
70%. 70. Yeah.
So in terms of calendar, the full array will be fielded when, you think?
Yeah, so there's a staged deployment plan. This coming winter, we're going to do the 30-40 gigahertz. Time permitting, the 150 gigahertz might go then, but it's a bit unlikely. It'll go the next year. And then the 95 will kick in either that year or the following year along with the dust monitoring channels.
Other questions?
Survey area, yeah. So this is the patch that we are targeting. I think it's a little less than 10% of the sky.
That's probably 2 or 3%.
2 or 3, yeah.
Yeah.
One question on the instrumentation front. 300 millikelvin and 4 Kelvin. How do you measure, or what device do you use to measure these temperatures? 4 and 300 millikelvin.
So there are commercial thermometers we buy that measure temperatures down to 10 millikelvin. this is not something, we don't think we just go to a website and just put an order and buy it. Is that what you were asking, or the detector? That,
What type of sensors?
the ruthenium oxide is one that works. Cernox diodes also do the job, yeah. But that is not the detector for the CMB, just to be clear. Yeah, that is to keep the fridge temperature.
One PTC per bore, is it? You've shown the cryocoolers. You have one per.
One per receiver.
So 4 of them are there.
That's right. Yep. In SPT, just to clarify, we had a second pair to cool down the whole optics chain.
Any other questions? Okay, if not, let's thank Rito again.